Lecture Bismillahirrahmanirrahim. Lecture 1 was related to the basics of heat transfer. In lecture 1, we have learned that what is heat transfer, how heat is transferred, in which direction heat is transferred, what are the different modes of heat transfer, and we found that there are three modes of heat transfer which are conduction, convection, and radiation. We have learned the different rate equations of conduction, convection, and radiation. In lecture 2, we are going to do some problems related to introduction of heat transfer. This lecture includes only numericals related to introduction of heat transfer. The first problem which we are going to do is problem 1-10 of Incropra and David 7th edition, and it states that a freezer compartment consists of a cubical cavity that is 2 meter on a side. Assume the bottom to be perfectly insulated. What is the minimum thickness of this styrofoam insulation that must be applied to the top and side walls to ensure a heat load of less than 500 watt when the inner and outer surfaces are at minus 10 degrees centigrade and 35 degrees centigrade? In this statement, we have a freezer compartment, and freezer compartment size is 2 meter by 2 meter. Freezer compartment is insulated by using styrofoam insulation, which has a thermal conductivity of 0.030 watt per meter Kelvin. If they if we want to assure that the heat loss is 500 watt or less than 500 watt, then what should be the minimum thickness of this styrofoam insulation if we want to maintain the inner side temperature at minus 10 degrees centigrade, and the freezer compartment is placed in an environment whose outside temperature is 35 degrees centigrade. Consider this is a freezer compartment. It is cubical in shape. This picture shows the schematic of freezer compartment. Six side. Side 6 is perfectly insulated, as stated in the problem that bottom side is perfectly insulated. So side number 6 shows the bottom of the cubical cavity. Side 6 is perfectly insulated. So heat will transfer from sides 1 to 5. Some important points which needs to be remembered, that the cubical freezer compartment shown in the figure, as I have discussed, that this cube shows the schematic of the freezer compartment. Bottom side is perfectly insulated, so heat loss will occur from 5 sides, which are 1 to 5, as shown in the figure. Heat loss through the freezer compartment is given by Fourier's law of heat transfer, which we have discussed in lecture 1, and it states that Q is equals to Ka T1 minus T2 over delta X, where Q is 500 watt heat loss from the freezer compartment. K is the thermal conductivity of styrofoam, and it is given in the problem statement that it is 0.030 watt per meter Kelvin. T1 is the outside temperature, which is 35 degrees centigrade. T2 is the inside temperature, which is minus 10 degrees centigrade. Here A is the area of the compartment. Each side has an area of 2 by 2 meter square, which comes out to be 4 meter square. Since there are 5 sides from which heat transfer is occurring, so the total area will be 20 meter square, and delta x is the required thickness which we have to find in this problem. We have put these values in equation of Fourier's law of heat transfer, that Q is 500 watt, K is 0.030 watt per meter Kelvin, area is 20 meter square, T1 is 35 degrees centigrade, T2 is minus 10 degrees centigrade. When we have put these values in the equation, we have found that the minimum thickness of the styrofoam insulation comes out to be 0.054 meter or 54 millimeter. If we applied styrofoam insulation of 54 millimeter thickness, then heat transfer will be less than 500 watt. This is what we have done in problem 1-10. Now we are going to do another problem, which is problem 1-15 of Incropra and Thavid. In this problem, the 5 millimeter thick bottom of a 200 millimeter diameter pen may be made from aluminum or copper. When used to boil the water, the surface of the bottom exposed to the water is nominally at 110 degrees centigrade. If heat is transferred from the stove to the pan at a rate of 600 watt, what is the temperature of the surface in contact with the stove for each of the two material? In this problem, we have a pan having bottom thickness of 5 millimeter and the diameter of the pan is 200 millimeter. The pan will be made from aluminum or copper. In short, we have two different cases. One is for aluminum and second one is for copper. The pan is used to boil water. The surface which is exposed to the water is at 110 degrees centigrade. The heat transfer from the stove to the pan at a rate of 600 watt, then what should be the surface temperature, the surface which is exposed to the stove? In both cases, we have to find the temperature of the surface which is exposed to the stove. Consider this is a pen having thickness of 5 millimeter. The diameter of the pen is 200 millimeter. Heat is transferring from bottom to top. The bottom is exposed to the stove, and at the top side we have water. So heat will transfer from bottom to top. The upside is exposed to the water and it is at a temperature of 110 degrees centigrade. We have to find the bottom side temperature. Again, Fourier's law of heat transfer will be used to define the heat transfer through the pen, which is Q is equals to Ka T1 minus T2 over delta X, where Q is the heat transfer from the stove to the pan, and it is given in the problem statement that it is around 600 watt. T2 is the upper side temperature which is exposed to water and it is 110 degrees centigrade. Area. Heat is transferring from the bottom of the pan, and the bottom of the pan is in circular shape having diameter of 200 millimeter or 0.2 millimeter. So the area which is perpendicular to the heat transfer will be circular area, and it will be given by pi by 4 d square, and it's come comes out to be 0.0314 meters square. The thickness through which heat is transferred is around 5 millimeter, which is given in the problem statement. We have to find the bottom side temperature T1, which is exposed to the stove. For aluminium, the thermal conductivity of aluminium given in the problem statement is 240 watt per meter Kelvin. We have substitute the value of Q, K, A, T2 and delta X in Fourier's law of heat transfer to determine the value of T1, which is the temperature of the surface exposed to the stove, and the temperature of the surface exposed to the stove in case of aluminium comes out to be 110.4 degrees centigrade. We will repeat this working for copper. For copper, thermal conductivity is given and it is 390 watt per meter Kelvin. We have to put the value of K in Fourier's law of heat transfer as we did for aluminium, and we put the value of Q, K, A, T2 and delta X. And for copper, the bottom side temperature, the surface which is exposed to the stove comes out to be 110.25 degrees centigrade. This is complete problem 1-15. Now we are going to do another problem, which is problem 1-21 of Incropla and David. An electric resistance heater is embedded in a long cylinder of diameter 30 millimeter. When water with a temperature of 25 degrees centigrade and a velocity of 1 meter per second flows cross over the cylinder, the power per unit length required to maintain the surface at a uniform temperature of 90 degrees centigrade is 20 kilowatt per meter. When air, also at 25 degrees centigrade, but with a velocity of 10 meter per second is flowing, the power per unit length required to maintain the same surface temperature is 400 watt per meter. Calculate and compare the convection coefficient for the flow of water. In this problem, we have a long cylinder having diameter of 30 millimeter. There is a there is an electric resistance heater embedded in the cylinder. There are two cases. In first case, water is flowing over the cylinder, and in second case, air is flowing over the cylinder. When water having temperature of 25 degrees centigrade and velocity 1 meter per second flows over the cylinder, the temperature of the cylinder is 90 degrees centigrade. So in order to maintain the temperature of 90 degrees centigrade, the power required per unit length is 28 kilowatt per meter. But when air having 25 degrees centigrade temperature but with 10 meter per second velocity is flowing over the cylinder, in this case the power per unit length required to maintain the temperature of 90 degrees centigrade is 400 watt per meter. We have to find the convection coefficients of water and air. That what are the convection coefficient for water and for air. This is a long cylinder having diameter of 30 millimeter. The temperature of this cylinder is maintained at 90 degrees centigrade. This is the fluid flowing over the cylinder. In first case, the fluid is water, and in second case, the fluid is air, and it is at a temperature of 25 degrees centigrade. We have to determine the convection coefficients for water and air. This will be the direction of heat transfer. That heat will transfer from cylinder to the fluid. In first case, remember, fluid is water, and in second case, the fluid is air. The heat transfer from the cylinder to the fluid will be governed by Newton's law of cooling, and it is Q is equals to HATS minus T infinity, where Q will be the heat transfer from cylinder to the fluid, H is the convective coefficient, A is the area perpendicular to the heat transfer, Ts is the surface temperature, which is the temperature of the cylinder, and it is given in the problem statement, which is 90 degrees centigrade. T infinity is the fluid temperature, that is the temperature of water in first case and temperature of air in second case, and for both cases T infinity is 25 degrees centigrade. The area which is perpendicular to the direction of heat is equal to the surface area of the cylinder, which is pi d L. In case of water, the heat loss is given in per unit length, which is Q dash is equals to Q over L, and it is 28 kilowatt per meter. Utilizing Newton's law of cooling, Q is equals to HW. HW refers to the heat transfer coefficient, convective coefficient in case of water, pi L surface area of the cylinder, because heat transfer will occur uh, in the direction perpendicular to the surface area of the cylinder. Ts is the cylinder temperature, and T infinity is the temperature of water. By just rearranging this equation, we have found that Q dash is equals to Q dash, which is the heat loss per unit length, is HW into pi d into Ts minus T infinity. In case of water, the heat loss is 28 kilowatt per meter, which is 28 exponent 3. HW, we have to find the value of HW. Pi is constant, diameter is 30 millimeter, so it will be 0.03 meter. Ts is 90 degrees centigrade, and T infinity is 25 degrees centigrade. When we solve this for convective heat transfer coefficient for water, it comes out to be 4570 watt per meter square Kelvin. Now, for air, Q dash, which is heat loss per unit length, is 400 watt per meter. Again, we will utilize Newton's law of cooling, and when we put the value of Q dash, diameter, Ts, and T infinity, the heat transfer coefficient for air is come out to be 65.3 watt per meter square Kelvin. This is all about this problem. Now we have another problem, which is problem 1-25 from Ingropra and David. A common procedure for measuring the velocity of an air stream involves the insertion of an electrically heated wire called a hot wire anemometer into the airflow with the axis of the wire oriented perpendicular to the flow direction. The electrical energy dissipated in the wire is assumed to be transferred to the air by forced convection. Hence, for the prescribed electrical power, the temperature of the wire depends on the convection coefficient, which in turn depends on the velocity of the air. Consider a wire of length L is equals to 20 millimeter and diameter D is equals to 0.5 millimeter, for which a calibration of the form V is equals to 6.25 exponent minus 5 h square has been determined. The velocity v and the convection coefficient h have units of meter per second and watt per meter square Kelvin respectively. In an application involving air at temperature of T infinity is equals to 25 degrees centigrade, the surface temperature of anemometer is maintained at Ts is equals to 75 degrees centigrade with a voltage drop of 5 volt and an electric current of 0.1 ampere. What is the velocity of the air? In this problem, we have hot wire anemometer which is used to measure the velocity of the air. The anemometer is heated utilizing electrical resistance heating by applying voltage of 5 volt and current of 0.1 ampere. The length of the anemometer is 20 millimeter and the diameter is 0.5 millimeter. The air temperature is 25 degrees centigrade and the surface temperature of the anemometer is maintained at 75 degrees centigrade. The velocity and h are related, and it is found through calibration that velocity is 6.25 exponent minus 5 times h square, where h is the convective heat transfer coefficient. We have to find the velocity of the air flowing over the anemometer. This is the hot wire anemometer having length of 20 millimeter and diameter of 0.5 millimeter. This is how air is flowing through the anemometer. The velocity of the air is calibrated and it's found to be 6.25 exponent minus 5 h square. The surface of the anemometer is maintained at a temperature of 75 degrees centigrade, and the air which is flowing over the anemometer is at 25 degrees centigrade. As I have mentioned that anemometer is heated by resistance heating, it means that heat dissipated is equal to the input electric power. That how much electrical power is applied to the anemometer, that will be dissipate as heat, and we know that electrical power is the product of current and voltage, so the heat dissipated will be equal to the product of current and voltage. And in problem statement, current is given 0 current is 0.1 ampere, voltage is 5 volt. The area which is perpendicular to the direction of heat transfer is again the surface area of the anemometer. Since anemometer looks like the cylinder, if we take any wire in our hand, and we will notice that wire is in the shape of cylinder, so the area which is perpendicular to the direction of heat transfer will be the surface area of the anemometer wire, and that will be the surface area of the cylinder, and it will be given by pi dl. The diameter of the anemometer wire is given in problem statement that it is 0.5 millimeter and length is 20 millimeter. When we put the value of D and L, we have found that area is 0.00003142 meter square. The surface of the anemometer is maintained at a temperature of 75 degrees centigrade, and air which is flowing over the anemometer is maintained at 25 degrees centigrade. Newton's law of heat transfer will be used to determine the convective heat transfer coefficient, and Newton's law of cooling states that Q is equals to HATS minus T infinity, where Q is the heat transfer from anemometer wire to the air. H is the convective heat transfer coefficient of air. A is the area perpendicular to the direction of heat transfer, and it is the surface area of the cylinder. Ts is the surface temperature of anemometer, and T infinity is the air temperature. Heat dissipated from the anemometer wire will be the electrical power, which will be the product of current and voltage, and it's come out to be zero point 0.5 watt. When we put the value of Q, A, Ts and T infinity in Newton's law of cooling, convective heat transfer coefficient comes out to be 318 watt per meter square Kelvin. Now the velocity of air is given by 6.25 exponent minus 5 times h square. We just put the value of h, which is convective heat transfer coefficient, in this equation, and velocity of air comes out to be 6.33 meter per second. Now we are moving towards another problem, which is problem 1-28 of Incrobra and Javid. An overhead 25-meter long uninsulated industrial steam pipe of 100 millimeter diameter is routed through a building whose walls and air are at 25 degrees centigrade. Pressurized steam maintains a surface temperature of 150 degrees centigrade, and the coefficient associated with the natural coefficient is H is equals to 10 watt per meter square Kelvin. The surface emissivity is epsilon is equals to zero point 0.8. Part A, what is the rate of heat loss from the steam line? Part B, if the steam is generated in a gas-fired boiler operating at an efficiency of 0.90 and natural gas is priced at $0.02 per megajoule, what is the annual cost of heat loss from the line? We have a long overhead industrial pipe which is 25 millimeter in length and 100 millimeter in diameter. The pipe is routed through a building whose walls and air are maintained at a temperature of 25 degrees centigrade. The industrial pipe is used to transport the pressurized steam at a temperature of 150 degrees centigrade. It means that surface temperature of pipe should be maintained at 150 degrees centigrade. The convection coefficient associated with it comes out to be 10 watt per meter square Kelvin. The emissivity of the pipe material is zero point 0.8. In first case, we have to find the heat loss from the pipe, and in second case, we have to determine the annual cost of heat loss from the line. If the boiler which is used to heat the steam has an efficiency of 0.90 and boiler is gas fired boiler and the price of natural gas is $0.02 per megajoule. This is the long steam pipe having length of 25 millimeter and diameter of 100 millimeter, and it is maintained at a temperature of 150 degrees centigrade. It is surrounded by air and walls, and surrounding is at a temperature of 25 degrees centigrade. Air is flowing over it at a temperature of T infinity equal to 25 degrees centigrade. So, heat will transfer from pipe to the surrounding in the form of radiation, and heat will transfer from pipe to the air in the form of convection. So, at the same time, two modes of heat transfer will occur, which are radiation and convection. The total heat loss from the pipe will be the sum of convection and radiation. Convective heat loss will be given as HATS minus T infinity, and radiative heat transfer will be epsilon sigma A Ts power 4 minus C surrounding power 4. H is the convective heat transfer coefficient, A is the area perpendicular to the direction of heat transfer, Ts is the surface temperature of the pipe, T infinity is the air temperature, sigma is the Boltzmann constant, epsilon is the emissivity of the pipe material, and T surrounding is the temperature of surroundings. H, A, Ts, T infinity, epsilon, sigma, T surrounding, all are given in the problem statement that convective heat transfer coefficient is 10 watt per meter square Kelvin. A will be the surface area of the pipe, and it will be pi dl, surface area of the cylinder. Diameter of the pipe is 100 millimeter and it is 25 meter in length. The pipe is maintained at a temperature of 150 degrees centigrade, and the air which is flowing over the pipe is at a temperature of 25 degrees centigrade. The emissivity of the pipe is 0.8. Sigma is constant, which is Stefan's Boltzmann constant, and it is 5.67 exponent minus 8. लास्ट स्लाइड में प्रॉब्लम आ गई, ट्रिम करूंगा. The total heat loss from the pipe will be the sum of convective and radiative heat transfer. The convective heat transfer will be HATS minus T infinity, where H is the convective heat transfer coefficient, A will be the area perpendicular to the direction of heat transfer, here A will be the surface area of the pipe will be pi dl, where d is the temp. Um, Ts is the surface temperature of the pipe. T infinity is the air flowing over it. The radiative heat transfer will be given as epsilon sigma A Ts power 4 minus T surrounding power 4, where epsilon is the emissivity of the pipe material. Sigma is the Stephen Boltzmann constant, A again will be the surface area of the pipe. Ts is the surface temperature of the pipe, and T surrounding is the temperature of the surrounding. The value of convective heat transfer coefficient is given in the problem, which is 10 watt per meter square Kelvin. The surface area of the pipe will be pi dl. The diameter is given in the problem statement, which is 100 millimeter or zero point 0.1 meter. The length of the pipe is 25 meter. Surface of the pipe is maintained at a temperature of 150 degrees centigrade, and the air is flowing at a temperature of 25 degrees centigrade. Emissivity of the material is zero point 0.8. Stephen Boltzmann constant is 5.67 exponent minus 8. The it is shown in this equation that I have put the value of temperature in Kelvin when I am going to solve radiation heat transfer. As we have discussed in lecture 1 when we were learning the radiation, that in order to solve the radiation heat transfer equation, we should put the value of temperature in Kelvin scale. I have put the value of Ts of 423 Kelvin. Ts was given around 150 degrees centigrade. When I put the value in Kelvin, it comes out to be 423 Kelvin. And same for the surrounding, that surrounding is at a temperature of 25 degrees centigrade. 25 degrees centigrade is equal to 298 Kelvin. So always put the value of temperature in Kelvin scale when you are going to solve radiation heat transfer equation. And convective heat transfer comes out to be 9817 watts, and radiative heat transfer comes out to be 8596 watt. The total heat transfer comes out to be 18,413 watts. Now, the annual energy loss from the pipe will be Q into 3600 seconds per hour into 24 hours per day into 365 days an year. The annual energy loss from the pipe comes out to be 5.8 exponent 11 joule per year. Now we have to find that how much energy is consumed by the furnace. The furnace has an efficiency of zero point 0.9. EF is the energy consumed by the furnace. So the energy consumed by the furnace comes out to be 6.45 exponent 11 joules per year. Now we are going to find how much cost will be saved if we apply insulation, or what will be the cost of heat loss, and it will be EF times CG, where EF is the energy consumed by the furnace and CG is the cost of generation. Cost save will be 6.45 exponent 5 megajoules per year. EF is 6.5 exponent 11 joules per year, or it will be equal to 6.45 exponent 5 megajoules per year. The cost of generation is 0.02 dollar per megajoule. So cost save will be around dollar 12,900 per year. This is all about the problems of like problems from lecture 1. If you have any query, then you can ask in online session. Thank you.